Yes. Yes. So now we will be doing the electric flux. So let's say, so what is electric flux? Let's say you have this area, right? Let's say you have this area and some electric, let's say this area is, let's say S, right? And some electric field lines are crossing like this, right? So the total number of electric field lines crossing through area is called the flux. This is electric flux. So total electric field lines passing through any passing through an area. Right. So this is electric flux, and what will be the mathematical form of this? So as I have written, this is E dot S or A, whatever you write. Okay, where this is the electric field and this is the area, right? And this is a vector, right? And this is a vector. So as you can see that this is the dot product of electric field and the area vector, right? So the first thing that we have to learn is that what is the direction of the area vector, right? So it is always normal to the surface. So let's say this is your surface, right? So this is your surface. So normal to the surface will be this, right? So this is the direction of the area vector. Let's say if you have the surface like this, right? So what will be the area vector? The area vector direction will be like this, right? And let's say you have the surface like this. So what will be the area vector direction? This will be the direction. Understood this point? Okay. So this is, as you can see, that this is in the XY plane, right? So XY plane has a normal which is in the direction of k hat, right? And normal to the what? Normal to the YZ plane would be what? Can you guess? So this is Y, this is X, this is Z. So this is the YZ plane, right? So the normal will be in which direction? I hat direction, right? And similarly, if you have the normal to the XZ plane, so that would be in the J hat direction. So this is the direction of the area vectors. If you have the area in the XY plane, so that direction, these are the direction of area vectors. Okay, understood up to this point. So now let me give you one question. Let's say in one question they are asking that, let's say your electric field is 3I plus 4J plus 2K hat, right? And your surface area is what? 2I plus 3J plus 4K, right? So if I ask you what will be the flux through this area, this will be what? Can you tell me? Yes. So 7 whole okay. Yes. So yes. Calculate and tell me what will be the answer. You know that electric flux will be simply the dot product, right? So you know that electric flux is a scalar quantity. I don't want to discuss that because you already learned. So flux is a scalar quantity, right? So what will be the answer? Did you find the answer? Please calculate and tell me. Yes. So what did you find? Okay. Yes. So yes. Okay. Okay. Sorry. Sorry. Yes. So what did you get? Still doing the calculation. 6i. Oh, so you see 6i plus 12j plus 8k. And did you forget the dot product? A was, let's say, 2i plus 3j plus 4k, right? And B is, let's say, 2i plus 3j plus 2k. So dot product will be a number, right? So 2i dot 2i will be 4i dot I. And I dot j will be 0 and I dot k will be 0. So, and then you have 3j plus 2i will be 0, 3j plus 3j would be 3 into 3 j dot j plus rest 0. And similarly, you get 4 into 2 k dot k. So as you have already learned that the dot product of two vectors is simply ax bx plus ay by plus az bz. So this would be simply, so this is 3i plus 4j plus 2k, right? And dot 2i plus 3j. So this would be a scalar quantity or vector quantity. This is a scalar quantity, right? So you can't have an answer like some ijk, right? Yes. So 3 into 2. So this would be 6. And 4 into 3, this is 12. And this is 2 into 4, 8. So this would be what? 26. So this is the answer, right? Understood? Because your answer will be not a vector quantity. It is a scalar quantity. Yes. So, so you wrote you wrote 6i plus 12j plus 8k, right? This was your electric flux. But you see that this is a vector quantity, right? This is a scalar quantity. This is a vector, right? So this can't be true. This has to be a scalar quantity, right? So this is a scalar quantity, right? Yes. So did you forget I dot I was what? I dot I was the magnitude of I, and cos of I dot I has 0 degree, right? So this is magnitude is 1, this is 1, and this is 1. So this was 1. And I dot j was I into j into cos 90 degree, right? So cos 90 is 0, so this is 0. So that is why we'll only get these type of solutions, right? Yes, so okay. Now let us do one more problem in which your in this problem the area vector will be not be given like the orthogonal or this kind of relation. So let's say your electric field is let's say 2I plus 3J plus 5K, right? And we have to find the electric flux through a surface in the, let's say, XY plane having area 2 meter square, right? So now tell me what will be the, so you have to calculate phi, and to calculate phi you need electric field and surface area vector, right? This you need. You know electric field which is electric field which is what? 2I plus 3J plus 5K, right? And you don't know what is the surface area. So you know that area is what? Area is 2 meters square, right? The magnitude of area is given 2 meters square. And what would be the direction? So normal to this XY plane. So what would be the normal to the XY plane? We discussed. So normal to the XY plane would be what? K vector, right? So can you tell me what would be the direction? So S vector will be what? 2, and what will be the direction? Will it be I, J, or K hat? It will be what? Hmm? Can you tell me? Yes. So, no, no. So you see that this is in the XY plane. So this is in the XY plane, right? So the direction will be the K hat, na? You see that, let's say you have some wall, right? And wall is in the X direction and in the Y direction. So perpendicular to the wall would be what direction? Wall is X and Y. So perpendicular to wall would be another direction, right? K direction. Yes, so it will be K. Understood now? Because we are calculating the normal to the XY plane is the direction of the area vector, right? Okay, so this is 2K hat. And now again, tell me if you have this vector, so what will be phi e? Calculate and tell me. Yes. So this will be Yes, so this is I dot k will be 0, j dot k will be 0. So you are left with k dot k. So 5k dot 2k will be how much? Right. So 2i, yes, 10. Right answer. Correct. Absolutely correct. So this will be 10. Okay. Because 2i dot 2k will be what? 2 into 2 and then I dot k. And we know that I and k is angle 90 degree. Is at angle 90 degree, right? So cos 90 is 0. Right, so this is 0. Okay, only this k and k will survive. Okay, now the next, so you calculated the flux, and now the next part is the Gauss law. Okay, so let me write it here. So Gauss law. So it says that the total electric flux in an enclosed area is what? Q enclosed by epsilon, right? So this is what Gauss says, that phi is Q enclosed by epsilon, right? Where this epsilon naught is the absolute permittivity of free space, right? So this is permittivity of free space. Permittivity of free space. Right, understood this concept. Any question in that? Yes, nice. So we have what kind of charge distribution? First, we will learn about what kind of electric field we have. Electric field do we have? So one is that we have continuous, and then we have discontinuous or discrete, right? So we have two kinds of electric field. Let's say for continuous, we have, let's say, volumetric charge, linear charge distribution, and then you have what? Sheet charge in on sheet, and then you have what? The cylindrical charge, right? These kind of charges you have. And for the discrete, you have, let's say, uh, charge 2 charges, 3 charges, something like that, right? Something like that. Okay, understood this part. So we use a Gauss law to calculate the continuous charge distribution electric field, right? So we can use Gauss law to calculate the electric field of the continuous charge distribution. Okay, so before I do that, first let us use some Gauss law. So let's say you have a charge like this. So charge is kept at the center, right? So let's say Q charge is kept at the center and electric field lines are passing from it, right? So one thing we know, right? One thing we know that the electric flux will be what? Q enclosed, which is Q by epsilon naught, right? This we know from Gauss law. Okay, this we know from the Gauss law, right? And if yes, yes, and if somebody asks you what would be the charges on the faces, so what would be the electric flux? Electric flux through the faces, right? This would be what? So how many faces are there? You have this face, right? And then you have then this face, right? And then you have this face, right? So you have how many total faces? And this one, right? So one, two, three, 4, 5, and 6, right? Yes, 6 phases are there. Okay, so the electric flux of six phases are how much? Q enclosed Q by epsilon naught, right? And if I ask from each phase for one phase, it would be what? Q by 6 epsilon. Right, understood this part? Understood? So yes, so now this charge was kept at the center of this cube, right? And let's say charge is placed in the corner. So let's say charge is placed in the corner of the cube, right? So the charge is placed at this point. Okay, so now if they ask you what would be the effective flux through this point, through the corner, right? So we will do what? We will this be covered with 6 cubes, right? So now we will keep this in the center. The center part we know, right? So we will do what? We will construct all the other cubes, right? And in here we will construct, and in here we will construct, right? So this would be in the center. Okay. So eight such cubes are needed. 8 such cubes are needed, right, to keep this in the center. Okay. So this would be what? Q by epsilon naught, right? So for corner, this would be what? Q by 8 epsilon naught. Did you understand this logic? Right. So let's say this was, let's say the charge was at this point, right? So charge was at this point. So you may kept one cube in here. You kept one cube in here. You kept one cube in here, one cube in here, and then this one cube here, then above. So you have total 8 cubes, right? So you put all those 8 cubes and then you will have a cube, big cube, which is whose charge is at the center, right? So whose charge is at the center. So you know that the flux will be Q enclosed by epsilon naught from Gauss law, right? So now we can calculate the flux from the small q, right? So for corner, this would be q by epsilon, 8 epsilon. Understood? Okay. Now the next question is like, so you had in the previous question, in all those previous question, you had some electric field like I, J, something like this one, which was not varying, right? Now we will calculate the electric flux for the varying electric field. So for varying electric field, right? So for varying electric field, you will have what? So let's say one question of this type is that, let's say you have this kind of question, right? And cube is kept like this. So cube is right. So this is the cube, and electric field is varying like this. This is varying like alpha a to the power x to the power half I hat, right? So this is how the electric field is varying. Okay, understand this much. So by looking into this expression, this expression, can you tell me what is the variation of electric field in all the directions? So Ex is what, Ey is what, and Ez is what? Can you tell me by looking into this expression? So can you tell me? Hmm? So this is in the I hat direction, right? So you only have Ex, which is alpha x to the power half, right? Ey is 0, Ez is 0, right? Because you only have electric field in the I direction, so only in the X direction. Understood? Yes. So now what will be the, so this distance is A and this is A, right? And how many we have to calculate the electric flux due to this part. So we have to calculate due to this part. Okay. So let's say you have this is one. So this is one direction E1. This is let's say phi 1. This is phi 2, right? And then you have up, phi up, and then you have phi down. So this is phi left, right? This is phi right. And then this is phi down. And this, let's say phi front and then phi backwards. So let's say phi, how should I? So let's say phi front and then phi backwards. Back. Okay, understood. So the total enclosed phi enclosed will be what? Phi total would be phi 1 plus phi left, phi left plus phi right plus phi what up plus phi down plus phi front and then phi back. Right? Am I clear? So so this would be the electric flux, right? Now what will be phi left? So phi left, you have this kind of surface. Let's say this kind of surface. Phi left is like this. So its electric field is in the direction of this way, right? Electric field is in the direction of this way, right? Ex, and this area is in the direction of this, right? So the angle between E and S is what? 180 degree, right? Am I correct? Yes. So what would be then flux? Flux is E S cos theta, right? Because E dot S is what? E S cos theta, right? So this is E X and S is how S is S area is, this is A and this is A, right? So this is A square and cos theta is 180 degree. So minus 1, right? And we know what is the X distance from here. So Ex is alpha X half A square minus. Okay. So this is minus A square alpha X we know. X is A, so this is A half. Right. So this would be how much? So this is minus of alpha A 2 plus half is 3 by 2. Right. So this is phi left. Understood. Understood this much. So this is phi left is minus alpha A 3 by 2. Right. And can you calculate what would be phi right? Calculate and tell me what would be phi right. Let me draw you the diagram. So this is okay. So this is the area and this is E and this is S, right? So S is A square I hat and E is what? You calculate and tell me what would be phi right. Just calculate and tell me what would be. Did you get the answer? This distance is how much? Yes. So what did you get? No, sir, I'm doing. Okay. 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 Hmm. Did you get the answer? Yes. All right. Um, should I help you? Can I help you? Okay. So let us understand this problem. Right. Your we have to calculate phi right. Right. So phi right is this one. So this is the surface area. Right. And this is the distance. X is 2a. Right. This is the distance from the X. And we know that how Ex is varying. Ex is how much? This is alpha x to the power half. Right. So this is the area. Area is what? This is some cube. Right. So A into A. And the direction of the area is in this direction. Right. So this is the normal vector of area. And what is the direction of the electric field? It is also in the I hat. So this is in the I hat. And this is E is also in the I hat direction. Right. We know that what is phi? Phi is E dot S. So we know that this is Ex I hat dot S is A square and I hat. Okay. So I dot I is 0. So we have A square Ex. And at which point we are calculating x equals to 2a, we are calculating electric field. So this would be what? A square and Ea is alpha x and half. So x we know. This is A square alpha and x is 2a to the power half. Right. So this would be what? A square into alpha into 2 to the power half and a to the power half. So again, 2 to the power half plus a to the power half is 3 by 2. So a 3 by 2, this is 2 to the power half is root 2. So root 2 a and alpha. And this is phi right. Any confusion in this? Any doubt in this? Okay, yes. Okay. Now we have calculated phi left. We have calculated phi right, which is what? Which is root 2 alpha a to the power 3 by 2. What about, let's see, what about the other part? So, so, so you see that for the up case, the area is in this direction. This is the area which is in the, what do you say? So this is xy up, so this is in the k hat direction, right? Okay. And this is in the k hat direction, down is in the minus k hat direction. but your electric field is in the x direction, I hat direction, right? So for phi up, this would be I into k, right? So that is theta is what? Theta is 90, right? So your phi up would be Es cos 90. And you know what is cos 90? So this is 0, right? So phi up is 0. Similarly, you have phi down, which is again 90. So this would be 0. Similar case for the front and the back. So in the front, you have what? In the front, okay, so up was J direction, not the up was J direction, right? J direction, and this is also J direction, but that is also perpendicular to I hat, right? Because this is I, this is J, right? This is J and this is I. Okay, understood this part? Yes, so this is J and this is minus J, right? What about this back? Back is in the direction of the minus K, right? And front is in the direction of this K hat. So again, these are perpendicular. So phi front would be 0 and phi back would be 0. So this 0. Understood? Any doubt in that? Any question? Okay. So now you are only left with what? Phi left and phi right. So you already calculated what is phi left and phi right. So your total flux would be phi left plus phi right only. So this would be how much? Minus of alpha A 3 by 2 plus of root alpha A 3 by 2. Right. So if you take common alpha and 3 by 2 here, so this would be minus 1 and this would be plus root. Right. So if you can write this like this, so alpha A 3 by 2 root 2 minus 1. So this is your flux. Understood? Understood? Yes. So, and now let us do one more problem, right? So what is so one problem was that, let's say you have the electric field like this, and this is the x y direction, and for greater than x, your E is let's say I hat, right? And for, let's say, x less than 0, for x less than 0, so E is minus I. Okay, so for x less than 0, E is, let's say, I hat for x greater than 0. Understood? Now we have to calculate what would be the flux through this area. So how many area do we have? We have 3 area, right? One, this is the second, and this curve is the third one, right? So how? Yes. So this one is the curved one, right? This one is the one surface, and this one is the second surface, right? Understood? Understood, Rufia? Yes. So the electric flux would be what? This would be phi 1 plus phi 2 plus phi 3, right? So this would be how much? So phi 1, let's say phi 1 would be E dot S, right? So you know what is the area of this surface. So this is the surface like, so this is the circular like surface, right? So and what is the angle here? So this is the angle of the surface area, right? So this is in the minus I direction. And you are calculating E less than 0. So for E less than 0, you have minus I here. So again, this is the direction of E. Okay. So minus minus gets cancelled. So this is positive. So this would be what? And your surface area is, let's say this is radius R. So this would be pi R square. Okay, understood? Okay, similarly, you can calculate phi 2. So for phi 2, this is the direction of the surface area, right? So surface area is what? Pi R square I hat. And what is vector E? This is iota hat for greater than 0. X is greater than 0 here. So this is x0 and x is greater than 0. So this is your E vector. So what would be phi E dot S? So I dot I is 1. So this would be pi R square, right? And for the curve part, you see that for the curve part, the surface area would be like this in this direction, right? So this would be always perpendicular to this or this electric field, right? Right. So, so this would be pi 3 would be theta is 90. So this is 0. Okay. So this is 0. So this is pi R square. This is pi R square. So this is 2 pi R square. Understood? Okay, now let us do the application of, okay, so this is the last topic. Okay, and then this will complete the chapter. Okay, so the last topic is the application of Gauss law. Right. Okay, so what, so we can use it to calculate the electric field. For in this case, we saw that, yes. Yes, so for this case, you saw that how can you use Gauss law to calculate the electric flux, right? So you saw that you can calculate the electric flux here, right? And in this question, we could also calculate, we could also have calculated the total charge here. So your phi was this, and this would be equal to what? Q total by epsilon naught. So you can also calculate the total charge here. So this would be what? Alpha and A 3 by 2 root 2 minus 1 into epsilon naught. Right. So you can also calculate the charges with the help of the Gauss law. But for the continuous distribution, you can also calculate the electric field. To calculate the electric field for continuous distribution. And what do I mean by continuous distribution? So let's say this line charge, this is infinite line charge, right? So this infinite line charge has some charges like this. Let's say plus, okay, right? So we can use, so this is the infinite. So this is the infinite long wire. Okay, so the Gauss law says that pi, so the total flux is what? Q enclosed by epsilon naught. And in the integral form, You can write also as the closed integral of this, right? This is Q enclosed by epsilon naught. Okay, right? And understood up to this point. So you have yes, so you have linear charge density, right? Linear, when I say linear charge density, linear charge density, which is we represent as lambda. So density we know, right? You know what is density. So density is something by, let's say, if you want to calculate something by something. Okay, density is like that. So if I say mass density, so this would be mass by volume. Okay, because I am taking volumetric mass density, right? If I say surface mass density, so that would be mass by area. Okay, and if I say linear mass density, so that would be mass by length. Okay, similarly, you have charge density. So charge density, which means that charge will be in the denominator, numerator. Okay, and if you have the linear charge, so this would be what? L. And this is represented by lambda, so lambda is Q by L. Okay, and if this is what? The surface charge density, so this is represented by Q by area. And this is represented by sigma. So sigma is Q by area. Okay. And you have another charge, which is volume charge density. So this would be what? Q by volume, right? And this is represented by rho. So rho is Q by volume, not the velocity. Okay, understood up to this point. So this is how you define the different charge density. Okay, so as I was discussing, linear charge density. So lambda is Q by L. So linear meaning that in this line you have some lambda and charges, right? So this is the length. So the total charge would be what? Total charge would be lambda into my L, because your Q would be what? This goes here, so Q would be lambda into my L. Okay. Now we will use the Gauss law to calculate the electric field for the linear charge density. So you have the Gauss law, which says that integral of E dot ds would be your Q enclosed by epsilon, right? Here, this is the Gaussian surface. This we have to keep in mind. So this is the Gaussian surface, right? And this we can take however we may like, right? So for the, let's say for linear charge, we will take a Gaussian surface like this. Okay, understood. So yes, so E dot ds would be what? So this is your ds, right? So E dot, and this is your what? Radius r, and this is the Gaussian surface, right? So the direction of the E vector and ds, this would be what? This is, let's say, perpendicular. This is parallel, right? So this is parallel. The electric field direction will be in this direction and your area vector would be in this direction, right? So this would be parallel. So this would be E constant and ds will be integral of ds in the closed, right? So this would be q enclosed and epsilon naught. So you can see that this is the shape of a what? This is the shape of a circle, right? And whose radius is r. So what would be the area? So this would be pi r square, right? And this is lambda L. Okay. Q enclosed is lambda L. This is upon epsilon naught. So this would be what? So this would be, okay. So I missed. So we should not take this. We will take the cylindrical. This this surface we will take, right? We will not take this this surface, right? So this is the Gaussian surface. Sorry about that, right? So this is the Gaussian surface, and what would be the area then? This is the length. So this is r and this is length L. Okay. So this would be what? This is the surface of the cylinder, right? So this would be E into 2 pi r and let's say L. Okay. And up to this much, So this is the length L, right? And the charge density, you know, that lambda is Q by L. Right, so you can calculate up to this length, Q will be lambda L. Am I correct? Yes, so this would be then lambda L by epsilon naught. Right, so this would be what? E would be lambda L by epsilon naught into 2 pi R L. So your L will be cancelled and you will get A E is equals to lambda by 2 pi epsilon naught R. Right, so this is the electric field for the infinitely long wire. Right, understood this much? Right, so you understand why did we take this cylindrical surface for the Gaussian surface? Because if we took this this circle, then this length will not be occupied, right? So we have to take this much amount of this length, right? To cover this much length, then we have to take the cylindrical type of. So this is how this is cylinder Gaussian surface. Understood? Okay, so the last topic. Yes, so this was the last topic, and the last electric field that we have to calculate is the electric field due to infinite sheet. Right, so this is right. So this is we have to calculate. Okay, understood? Okay. So the electric field of so we will take this is this sheet which has some surface charge distribution. right? So this has some surface charge distribution, okay? And the electric field will be what? If you solve, then this would be directly, I am directly writing, and you try to figure out why this would be the case. So electric field due to this would be the magnitude. So electric field due to this would be sigma by 2 epsilon, right? And this would be in this direction and in this direction, right? So this is the electric field due to infinite sheet, and this is the electric field due to right. So sphere is not in your syllabus, only infinite sheet, and this is in your syllabus. Okay. So this completes finally this completes our electric charge, and from the next class onwards, I will be talking about electric potential. Do you have any doubt up to this point? Okay, so Alam, okay, so let's meet on what in the next class, and then we'll start the second chapter. Allah Hafiz. Bye, bye, Allah Hafiz.